Hi all, thanks everyone for attending the third episode of the Power Hour series, where we're going to be continuing the electrical asset management process on in understanding transformer oil testing and sampling. I am Daniel Henderson. I'm going to be one of your hosts today. I'm the Global Head of Electrical Safety here at Scanware. For those that don't know me, I'm a chartered electrical engineer based in the UK with a varied background in electrical engineering and electrical safety. I'm joined today by VPS Power, Andrew Jenkins and Ryan Burgess. So I'll hand you over them to get some introductions.
Hi, I'm Ryan Burgess. I'm Technical Manager here at VPS Power. I've been in the industry for over 15 years. And yeah, that's me in a nutshell. Andrew?
Yeah, hi, good afternoon. My name's Andrew Jenkins. I'm the Senior Technical Advisor here at VPS Power. I've been in the industry for 25 years, beginning my career as an analyst to the job that I do now, which is diagnosis and technical advice to customers.
So a little bit about VPS Power. We've been around for over 40 years. We are an independent testing and advisory service specializing in electrical insulating oils. We work with a variety of different industries and client types, ranging from power generation, with the renewable sector, through to distribution network operators, transmission network operators, O&Ms, manufacturers, installation companies, maintenance companies, and even manufacturers of goods, not just the transformers themselves. And we are a global company of approximately 400 members of staff. And yeah, and we've got members that are on the BSI GEL 10 committee. Next slide, please, Dan.
Thank you. And just some housekeeping. So you will receive the slides after the webinar via email if you're registered. You will get a recording sent to you as well after the webinar. On completion, there will be a post-webinar survey. Please tell us how we did. We have got some topics coming along, but we have been taking some feedback from what's been coming in the last sessions to include them in future sessions that are coming up. Please use the Q&A throughout. Any questions we will try and answer at the end. And if you do want to be automatically registered for any future ones, please let us know in the chat and we can arrange that as well. So just to give a bit of a recap and an overview of the series itself. So this only goes up to the end of the year, but it will continue in deep. So it's difficult to do in single sessions. So the plan is that we're going to do this as a bit of a journey. So whether you're an energy marshal or an electrical duty holder, responsible person, licensed electrical worker, if you've got management responsibilities for electrical networks or maintenance on electrical assets, then this is who we're trying to support and build your knowledge. So we started off with when you first start out, what the roles and responsibilities are, what your responsibilities cover in line with legislation, and then building up that basic asset data. So building up the asset lists, how it's important, so how it's good to identify operational restrictions and what they are, and then how to use that to then build up maintenance plans, which we went into the second session, which was all around how to build a prescriptive maintenance plan and where there's grey areas between the guidance and legislation, then how to tailor it for your environment. So we've continued that on today, where we're going to bring that into specific assets, so understanding transformer oil sample testing, why it's done, and then get into interpretation of the results. So from experience, a lot of people who go into things like facilities management or into electrical duty or responsible person roles, often it's a bit of a jump up. So they might have had some interactions with looking after distribution equipment and things like that, but often they haven't as well. So it can be quite a steep learning curve. So the aim of this is to try and widen the knowledge there and give some understanding around what you do and interpreting the results, and then understanding why it's important, how it links to electrical safety, and then some potential mitigations that you can then look into. And then just to finish off, the next session is going to be a bit of an interactive one with another collaborative partner, where we're going to look at a practical overview of protection studies, so protection, coordination, fault level, and arc flash outputs, to discuss how those impact electrical safety and reliability of your networks and what those crucial changes make. And then finally, we're going to finish the year off by trying to do a live root cause analysis around a failure of electrical equipment. So just to cover some the learning objectives of today, We're going to look to understand the importance of transformer oil testing and the standards that apply, why it's important. We're also going to gain insights into the tests conducted on transformer oil and the impact that they can have on electrical safety and the reliability of your assets. And then we're also going to look at how to interpret those oil sample results, identify possible causes of issues, and then how to implement possible mitigation strategies to protect your assets. I'll now hand you over to VPS.
So first, we're going to look at the importance of asset management. So effective asset management is essential as it ensures reliability, safety, and effective distribution of the power within your system. Whereas poor asset management can lead to outages and safety risks. And there's a strong link between good condition monitoring and preventative maintenance in increasing the life of the asset and also the reliability. And this is just an overview of the other possible options. Next slide, please, Ben.
Yeah, so just before we start, it's just a general question for the people on the call. So how often do you test your transformer oil? You should have a poll come up, and if you can just give us some feedback. We're just trying to understand how often people do this, and then hopefully we can understand what that's based on. Sure, you'll have rationale based behind that.
Let's give it a couple more seconds, Dan, give people a bit of time to get the notes in.
Yep, no probs.
Give it another
Think-
5 seconds. 3, 2, 1. There we go.
No, that's good. It's an interesting mix. I expected most of them to be in that annual, because that's where a lot of the recommendations are around the annual side. Sometimes it's 6 monthly, but again, that could be based upon recommendations. And then the interesting points, which would be good maybe to get some feedback in the chat, would be around the others. Never is probably if they haven't got any oil filled assets, if they've got maybe dry type cast resin transformers. And the others, I'm hoping they come down to a condition-based approach where they've got maybe online monitoring or some predictive techniques where they're doing it as and when things are arising or when they have changing conditions. But it'll be interesting if people in those brackets, if you can maybe put in the chat why you do it to those other frequencies other than annual and 6 monthly. That'll be appreciated. Now we'll see how long it takes to change to the next slide. There you go. Back to you, Ryan.
Yep. So when it comes to transformer fluids, there's 4 main options out there that you can use. First of all, you've got mineral oils, then you've got synthetic esters, natural esters, and silicones. All the fluids perform essentially the same jobs. It's just certain situations where you may choose one over another. So, for example, if it's an asset that's in an indoor space and you may go with a synthetic ester due to it having a higher flash point and fire point, meaning that if it does catch fire, it takes a lot higher temperatures for that fire to catch hold. And as well, in turn, you can then make the transformer smaller because you don't need as much of the fire prevention systems as you would with a mineral filled asset. So let's look at the purpose of the oil. First and foremost, a transformer oil is an insulator. So what do I mean by that? So as an insulator, they control the flow of the electricity, preventing the current from jumping between winding to winding or from the core to the winding, which ultimately can cause short circuits, leading to reduced life of the transformer. Then it acts as a coolant. So as a coolant, it carries the heat away from the core to the exterior of the transformer. This is done usually via convection currents, but in larger transformers, pumps can also be used to pump the heat away in the oil from the core to the exterior. This in turn allows for safer operation of the asset and a prolonged life of the asset. And finally, it's a great preventative tool, just like a blood test. By testing it, we can determine what's going on with the oil and the asset itself. So why does it need testing? From the testing, we can determine what type of faults are happening. So if there are electrical or thermal stresses within the transformer, and as the oil degrades, those cooling and insulating properties are reduced. So by testing, we can monitor them over time to see if they're still effective or if they are deteriorating. And that's ultimately what we're here for. Next slide, please.
Yep.
So we're going to look at some consequences of not performing asset management. So let's take a real world example. You had the North Hyde fire in March this year, which was due to a bushings failure, which is what these pictures simulate. That bushings failure was due to elevated moisture, which was first identified in July 2018. Maintenance was due to be performed in 2022, which is when it deferred, which ultimately led to a catastrophic failure of that transformer, which led to approximately 300,000 people being delayed at Heathrow, and obviously ultimately causing large financial losses for the airlines and small businesses, and reputational damage to both the national grid and even Heathrow. And they're just the extreme cases. I believe that we've now got a short video just to show an example of a bushings fire.
Yeah. So just to give us some context around the amount of energy that's there, and obviously where we've covered the flammable properties of oil, which probably will be quite heavily documented in like your loss prevention and risk management guidelines or your insurance requirements. Obviously, if it's sustained and if there's still a fuel source there, then it's potential that it could go on for a prolonged period of time.
And luckily that was an unmanned site, and especially with a bushings fire, bushings are made from ceramic, and as they explode, it's just like basically a lot of shrapnel getting thrown around and can cause a lot of damage.
So just whilst we're on the subject, before we go into the testing, just again, a general question, if you've ever experienced a transformer catastrophic failure in your workplace, or if you know of one within the business, and it's purely just, again, to try and understand if people on the call have and understood and felt the impact.
Give it another couple of seconds, Dan. 3, 2, 1.
That's good. Good that a lot of people haven't experienced it. To those that have, I mean, hopefully there was no one in the vicinity, because obviously a catastrophic failure of a transformer can have massive consequences from a safety perspective. If no one was in the vicinity, again, there's the near miss potential that someone could be in, but probably the biggest one that we have experienced, those of us that have had a transformer failure, is the business impact. It's normally quite a long process to try and identify the root cause, try and get any remediation to get everything back up and running. And often, when it's adjacent to things, it causes prolonged damage to other things in the area, cabling, possibly back to the circuit breaker. So the business impact alone, the downtime, is normally the impact that we take away once we've providing there's nobody in the vicinity. Obviously, safety is the biggest concern. But yeah, it's just understanding what those impacts look like. And I was just trying to understand and gauge whether people had any experience of that. Okay, we'll now go into testing, or the standards for that. I'll pass you back to VPS.
Yep. So here at VPS Power, we follow the latest version of internationally recognized standards for both fluid quality and interpreting a DGA, or dissolved gases. When it comes to the DGA standards, they're not actually standards, they are guidelines. So by that, we mean they don't have hard and fast limits due to the way the data is collected by the IEC. They give you a range, and it also allows for certain types of assets operating differently. So you can't have the same specification just by saying a transformer. You can't just say this one limit for every transformer. Just on, haven't made a note here, but just to make a note, when it comes to sampling and the reports issued are only as good as the information that we receive and also as good as the sample. So all sampling should be done in following guidelines set out in IEC 60475. And that's that on specification. Unless you've got anything to add on specifications, Andrew?
No.
So in terms of testing, there are lots of varying tests that can be formed, as you can see from this slide here, and different degrees of suites that can be done. So the IEC themselves break down suites of tests into 3 categories. First of all, you have routine testing, and the routine testing is the minimum essential checks that should be performed to ensure good fluid quality. And that is covered in the fluid assessment, or routine, as what we call routine. Then you have your complementary tests. These are additional tests that are added to make the data from the fluid quality or the fluid assessment to give you further information, especially if you're starting to see degradation. You can then monitor it better through those complementary tests. And then finally, you've got investigative tests. These are predominantly used to provide compliance to environmental specifications or operational requirements. And today, all the testing that we're going to talk about would be covered under the routine DJ and paper assessment, which for the information it gives you is the minimal amount of information that you need to determine how the asset is operating and aging through the DJ and the paper assessment, and how the fluid itself is doing over time. And that's it on test suites. So first of all, we'll look at water testing. So water testing is probably, of the fluid quality tests, the most critical test to understand. So understanding water and why it's, sorry. So it's important to understand how much water is present in a transformer, as the presence of water reduces the insulating properties of the oil, and it also speeds up the aging of the oil as the water increases. So why does each fluid type, as you can see, have a different specification? It's all to do with the polarity of each fluid. So a mineral oil has the lowest polarity, meaning it can absorb the least amount of water before becoming saturated and ultimately reducing its insulating properties. Whereas if you look at something like a synthetic ester, that's at the complete opposite end. That has a significantly higher polarity, and due to that, it's able to absorb larger amounts of water before those properties are degraded. So when it comes to looking at the results, no matter the fluid type, a low water content is good and indicates that the fluid itself is still effective, whereas a high water content is showing that the fluid is poor and starting to degrade, and those properties are reduced. So where does the water come from? There's a number of different sources. First of all, it's from something as simple as somebody leaving the breathers themselves being oversaturated, and the water is then ingresses through the breathers. And from the actual inside itself, if somebody's done maintenance and just natural moisture, it's not been dried properly, that can then ingress from that way. That's it on water.
Yeah, and then just to continue that on, so again, as Ryan's mentioned, the links that has is obviously the higher water content, the lower the reduction in dielectric strength, and you've got the potential there to conduct. So in the event of increased water content, there's potential there of resulting in flashover. as we've kind of seen with the bushing side of things, with that being one of the things that was detected in the previous sample. So again, there's lots of different causes. As I mentioned, it could be an integrity issue. So any fittings or connections, which might be on the radiators or pipework, the sight glass, the conservator. So in that example there, picture, you can see there's a leak in sight glass. Potentially you could get water ingress there. The breather on free breathing transformers. So this is such a common thing that I see on sites where I go and do a site inspection, and I'll see that for something that's such an easy maintenance task, it's neglected. So free breathing transformers, they're designed so that as the temperature increases and decreases, the oil level expands and contracts, and those desiccant breathers will allow that pressure to be pushed out or in as the oil contracts or expands. And obviously any moisture in that environment, so whether it's humid, whether it's wet outside, cold and damp in that space, that silica gel breather, that desiccant breather is there to absorb that moisture, so nothing should get into the transformer. Likewise, where you're getting any evaporation inside the transformer, it should be able to escape through and get captured within that breather and not held in the oil. So that's what that's there for. As that saturates, as you can see in that picture there, that was originally orange, and then when that's absolutely saturated, there's nothing that can get in or out. So that moisture can get absorbed then into the water. So it's such a common thing, which costs pounds or dollars to fix, or in reality could end up costing you either business downtime or tens of thousands of dollars if you've got to replace the asset. So it's such an easy thing. Another thing that I've experienced is the transport method. So where I've had on first oil sample test of a new transformer, water content, and you can go back to the factory filling. I've had it where the batch sample that filled the transformer was all fine, but when it's been transported to site for installation, whether it's in a construction project, the radiators might be transported separately, likewise the conservator, the pipe work, and as they're installed, if it's not done in a satisfactory environment, there's potential there where you could get water ingress, which again can be difficult to detect and pin down where that happened if it's not tracked and done properly in the installation phase. And then finally, I mean, there's many other possible causes, but the sample conditions, the most common thing that I'll see is you'll get a recommendation back saying water content. And often if you're using the same lab or tracking your results, which is really good to do, you build up that asset history. So if you haven't had any water ingress before, then suddenly on a sample report, you've now got water ingress. There's been that fundamental change. So that often the actions are resample as soon as possible. And often on that initial resample, it comes down to the sample conditions. So it might be raining on the time, it's such a common thing, or the actual sample equipment has been contaminated by water somehow, possibly by weather, possibly by storage, but often that is a key thing that happens. And then key outputs typically is to inspect the asset, see if you can identify signs of the ingress, the breather condition, as we've mentioned, and then if you can identify it, it is potential where as a mitigation, you can go to a reputable oil company and they can cycle the oil, where we can take the asset offline, cycle the oil through a drying process and reduce that moisture through coalescers and pre-filters to then and in heat to then put it back in a reconditioned state. We will come back to this to understand. You do have to have further information because if some of the other conditions of the transformer aren't correct, when you're doing this process of recirculating the oil, you can actually cause more damage as well in the process. So an example that I've experienced is where there was an increased parts per million, and the more that this was done, which the client insisted on, we were recirculating the oil, and ultimately that it was just degrading the paper insulation on the winding. So it's just important to be mindful of that.
So let's now have a look at the acidity and why that's important. So what is acidity, or why do you need to do it? So an acidity measurement helps to understand the condition of the fluid and how it's degrading over time at a basic level. So as you can see from the specification there, that each fluid type has its own completely different limit. And the reason for the different limit is, again, due to the types of acids that are formed during the aging process. So again, we're going to just compare mineral oils and synthetic esters. So mineral oils produce shorter chained acids, which are more readily absorbable in the water, which are then more readily absorbable into the cellulose insulating material. So meaning that you need a smaller amount for them to be more harmful, whereas esters produce longer chained acids, which don't readily absorb in water. So because of that, you need a higher amount of them to become more damaging to the paper over time. But again, the basic principles when you're looking at that data are a low acidity is good and shows that the cooling and the insulating properties have not been degraded yet, whereas a high acidity suggests degrading, and obviously the ability of the oil's properties have been reduced over time. The source is just general time and aging. That's the main source of it, why it appears, and it's one of them. As it starts increasing over time, it just starts going up and up. So it's just one of them. It's a time factor.
Yeah, and the impact is obviously that it's going to deteriorate your insulation on your paper insulation typically on your windings will start deteriorating and then ultimately resulting in a failure if it's not addressed in a quick enough time. But again, those similar mitigations, so resample, make sure that it is from the sample. You can monitor if it's in low amounts initially, monitor until it increases, but then obviously you can start looking at things like possibly changing the oil out or recircling the oil to a suitable condition. But there are mitigations out there. But again, it's important to have that whole picture before you choose what mitigation strategy you're going to do.
We've just got something else to add before we move on. Go on, Andrew.
Yeah, so the consequences of having high acidity means that it has the potential to form sludge, and the sludge collects on the windings and other parts of the transformer and reduces its insulating properties.
That's one thing we did forget to add was the sludge. Next one, unless you've got anything else, Dan.
No, that's great. Thank you.
So from the fluid quality tests, we'll look at the final test, and that's breakdown voltage. So breakdown voltage can also be known as dielectric strength, depending on who you speak to. It's the same thing, just a different term. Breakdown voltage is the measurement of the fluid's ability to withstand an electrical stress without it failing. So what causes that to fail? It's usually particulates in the fluid, but it's also linked to the moisture as well. And it's an early warning sign of the degradation of the fluid as well as the water and the acidity. So what causes that drop? As I said, the main drop in that performance is due to the moisture and other contaminants. So the basic remedy usually first time is to take a resample. As Dan was saying, that's usually down to a poor sample, whether if it's you've not cleaned the sample point correctly, you've taken the sample in the wet, or you've just used dirty equipment. And then in terms of looking at what the results show you, high breakdown voltage indicates good dielectric strength, which indicates good insulating properties, whereas a reduced or a low breakdown is a reduced performance in dielectric strength and in insulating properties.
Yeah, I mean, this is the important bit is just to make sure that you're doing the right tests to against the standard. So a company that I'd done some work with, they'd done testing against their own internal standard that they kind of passed down over time. And it was purely water content and acidity, and essentially a flash test. And they did that against a standard, not an international standard, just against their own that had been done internally. And when a sample was done a couple of years ago, that initial sample against these or against the standard for that geographical location, it was identified on a lot of their assets that they had a significant breakdown voltage reduction on on most of their transformers. So they were 11 kV assets as an example, but most of those were down to sort of 16, 17 kV. When you think of all the standards saying less than 30 kV. But this is you know, once you start getting down towards your nominal voltage, you've got that massive increased risk of, well, it's not an insulator anymore. It's going to conduct, so you're straight into that flashover territory. So it's such an important thing to make sure what testing you are doing is against a recognized standard, or at least the standard for your geographical location.
So that's the end of fluid quality. Now we're going to look at dissolved gas analysis, known as DGA for short. So DGA is probably the most critical tool in determining how the transformer or the electrical asset itself is performing over time, as it's used to determine the condition and the health through analysing the gases present to determine the types of fault, if they are present. So on the next slide, this will cover what gases and that we look at. So there are many gases that can be analysed through DGA. First, we'll look at the combustible gases. So you've got hydrogen, methane, ethane, ethylene, and acetylene. Carbon monoxide is classed as a combustible gas. Then you've got your non-combustible gases of carbon dioxide, oxygen, and nitrogen. And depending on the ratios and the amounts of each gas present, we can determine what kind of faults are present, such as arcing, overheating, and insulation degradation, which the next slide will explain a lot more. So interpreting the faults from that test and what they mean. So there's many different models that can be used to interpret your data. Here at VPS, we use predominantly Duval's triangle and Duval's pentagon. But no matter what tool you're using, the basic principles are the same. So hydrogen is typically the first gas to appear when there's a fault, which is an early indicator of faults such as partial discharges, low energy arcing, and a non-fault phenomenon known as stray gassing. Then you have methane, which is a low thermal fault indicator, and that's typically reduced due to things such as basic overheating. So that overheating can be due to poor circulation, or something even as basic as there's a load of debris around the transformer on the outside, especially here in the UK this time of year, all the leaves left blocking the radiator, so the heat isn't effectively distributed from the external of the transformer like it should be. Then you've got ethylene. Then you've got ethane, which is a medium thermal fault. That's typically generated at internal temperatures of 300 to 700 degrees C. And again, is an indicator of more moderate thermal issues or higher levels of overheating. Then you've got ethylene, which is produced at temperatures of over 700. These are known as high temperature thermal faults and are due to severe overheating and potentially due to insulation breakdown. So, and finally, of the combustible gases, you've got acetylene. This is an indicator of high energy faults such as arcing, which can lead to significant damage. Of those gases that we've just talked about, they're all in their own, all when they're present isn't a good thing, but acetylene is the one that's seen as the instant, once you see it, you need to take action, but they're all important. It's not just acetylene. And then finally, you can also use the oxide gases, which are the carbon monoxide and the carbon dioxide. Based on their ratio, that can determine how the paper insulation itself is degrading over time. It won't tell you the strength of the paper, we'll cover that in a moment, but it will tell you that there's degradation. And depending on the ratios, you can determine if it's due to overheating or just general aging. So next, well, just before we move on, the next thing we'll be looking at is furans, which will explain better that oxidation, the oxide side. You got anything else, Andrew?
No, that's fine.
Just to add on to that, onto the DGA side, as Ryan mentioned, this is probably one of the most important tests that you can do to understand the asset's health. It's a really good snapshot to understand how the transformer is, how it's operating, any issues internal, and this is probably one of the most overlooked tests that I see. So often, I mean, prices between the tests, as we've covered, you've got the fluid quality stuff, then you've got your additionals, and because this is an additional, it's marginal really, the increase. Doesn't matter what vendor does it, all the prices are marginal on top of that. But for whatever reason, this is just one of the most, whether it's cost or whether it's knowledge, it's always one of the most overlooked tests. So it's just one. It's often it's in the a lot of loss prevention and risk management standards. It's definitely in FM Global as a recommendation. If most people adopt that as your insurance method, is to conduct DGA as part of your regular maintenance. But yeah, so some of the reasons why this can happen is you can have potential significant load changes or significant load. So if you're overloading your assets, as Ryan's mentioned, that can be a contributor. The load type. So if you've got a large non-linear load, so a lot of variable frequency drives or variable speed drives, or inverters, potentially that can put a lot of non-linear load onto the which culminate back in the transformer, which we'll cover in another session next year on power quality and the impacts that has on the transformer health. But again, this is a massive contributor to essentially overloading the asset, which results in essentially this internal fault given away by the DGA results. An internal fault, again, the design's been very similar, for a long period of time. So if you look at it, transformers are a good design. They're quite robust, but there are parts in there that can fail over time. Tap changes probably one of the lead contributors on most times that I've had sampling done, and something's come back to have a thermal fault in the transformer. Although they're quite substantial, there are some less substantial parts on there. It's essentially a rotating cam between contacts, and the pictures that I've got shown there. So this is again someone that I worked with in the past, where they had done the basic fluid samples, and then they didn't do DGA, and ultimately this tap changer in the bottom right corner failed, and this was a catastrophic failure of the transformer. You'll see there where you've got a lot of carbon buildup on the tap changer. This is obviously inside of that oil tank, and then this here, right in the bottom corner, this is the termination that went from the HV box to the tap changer. So this was, this was blown through. This was another area where we're getting this arcing. So again, if they had been doing DGA in addition to the other tests, this would have been picked up relatively early, and it would have been a relatively simple fix, or at least it could have been identified and planned in rather than the significant downtime that they experienced. And again, so actions, resample, make sure that it is correct. It's important to try and trend these things, so make sure we've got that data build up so we can actually see, is it as is it building? Often you can get significant swings, especially when you've got things like solar or PV. Potentially you can get significant load changes where you get builds up of certain gases, which can then also either steady out or dissipate. So we can have certain conditions on certain assets. So it's good to understand what you've got and how it operates by understand the sampling, understand the load. Obviously, if you have got something happening in the transformer, as Ryan said, we can get an indication from the types of temperatures, that can be expected because of the types of gases that are in there, to try and pinpoint where it might be. But you can potentially do some non-invasive inspections, things like partial discharge surveys, to try and identify if you have got any internal issues and where they might be. And then obviously invasive. So we've got a picture there of the transformer that's being partially drained down, then the lid removed, to try and do an inspection of what's there, to identify where that issue is, in order to identify the defect and then remedy that defect. Again, linking back to the first one, we've got to make sure that the conditions are good and that we control the transfer of oil, so that we don't put any pollutants into that transformer, any debris, any water content, things like that. So we need to make sure we do that right. And then there are options where we can potentially then drain that oil out, flush it, and then conduct an oil change. But the biggest, we have to fix the issue first. So I've seen this so often, where people have fed back to me to say, you know, we've had high DGA on this transformer, and you know, we only changed the oil last year. You know, this is common feedback that I get, and not to take anything away from anybody, but ultimately it's not the oil's fault. The oil's there, as Ryan said, as an insulator and as a cooling medium. It's there to help that asset operate. It's not the oil's fault that it's got dissolved gases increasing in there. There's an internal fault within that transformer that's causing that. But this is common. This is a common thing where certain vendors will just change your oil, which is quite a significant cost, and obviously it doesn't fix the issue. So make sure you understand the issue and before you conduct your remediation of changing your oil out. Back to
So we'll look at the
VPS.
final test that we're going to talk about today, and that is fuel analysis and estimated degree of polymerization. So over time, as the insulating material inside breaks down due to heat, moisture, and chemical reactions, basically the stuff we talked about earlier, furans, or a compound known as furans, are released from the cellulose material, and we're able to detect them, the quantities of them, to determine how the asset itself is aging over time. Because essentially the strength of the paper is the health of the transformer overall at a basic level. So there's two ways you can determine the strength of that paper. You can either do a physical DP analysis, which would require de-energizing the asset, draining the asset, taking several cuttings from the windings themselves, and then sending them off to a laboratory for physical testing, which is a very expensive task. And as well, when you're taking samples, it's not just one sample you need from that winding, you need to take several samples, as each layer of paper will be degrading different over time. The best way to do this is through furan analysis and the estimated degree of polymerization. As one, it's significantly cheaper, and two, it doesn't cause damage to the asset. That damage, if it is detected, has already been performed, is already happening internally. You're not adding to that by going in, taking a physical sample. So here at VPS, we use a model known as Chendong, and we use the analyte 2-furfural, also known as 2-fal, to calculate that aging process. So as you can see at the bottom here, we have a list of numbers. This isn't a specification. There isn't an internationally recognized specification out there. This is just these, I'll call it a specification, but this specification is based on guidelines from multiple sources around the world. So as you can see, anything with a DP of over 400 would be a pass, indicating that the asset is still in good health. But depending on whereabouts on that range it is, we can determine how well it is. So just because it's well or in good health doesn't mean it's perfect. Then you're getting into the caution range, the 400 to the 250. At this point, this is where you then need to start thinking about upping your frequency of testing. So if you're testing every 2 years, you'd want to consider upping to every year to carry on monitoring. And then once you get to the 250 or higher, again, there's different levels even past that. And when you get to the action, you need to start planning for the end of the asset's life. And during that period, from caution to action, you also need to consider managing the load of an asset. So if it's an asset that's used to going from high load, low load, high load, low load, you definitely want to reduce that. Or if it's at a constant high load, you want to reduce the load and the stress that it's under to help prolong the life of that paper. But ultimately, you need to also look after the oil itself, as we said, as that starts degrading, that will speed this up as well. But it's not just a simple case of then, oh, we'll put new oil in, because it's also at that point, you're going to lose the information that you've collected from the aging process, and it will reset. So the data will go, oh, your furans are back to normal, but you've just lost all your data because it hasn't had time to re-equilibrate. So your paper is still aged. Just by replacing the oil, you're not replacing the paper or re-aging the paper. Have you got anything else to add on furans, Andrew?
Yeah, so we put a value of 250 on there. That's the value we use at VPS. I mean, it's a conservative estimate. Probably 150 is closer to the mark, although when it gets to that level, the transformer can still operate normally for many years. But if it's exposed to external events like lightning strikes or mechanical shock, it has a higher risk of failing.
This one was for you, Ben.
Yeah, yeah, so again, just to add on to what Ryan was saying before, it's good to understand the differences across the different tests and how they kind of interact as well. So it's good to, like we covered before, just for furans, if we were just doing water content and we identified we had water in there, or we were actioning that as part of our mitigation, if we didn't have furans, so we didn't understand what what was going on inside there from sort of like paper debris being in the oil, any breakdown or increase in acidity. Obviously, if we went into like a remediation, like recircling the oil, there's potential there where we could then rapidly increase that process by actually forcing, forcing the process by possibly pumping across or drawing away across the windings, drawing out more paper or causing an increased aging process. So again, it's good to understand that all the results, how they tie in, and then using that information to determine what your remediation actions are.
So here at VPS, our reports follow a basic traffic light system. So a green indicator on the report shows that the fluid quality, the paper insulation, and the asset itself from the gases point are in an acceptable condition, and you don't need to take any further action other than whatever you've got planned for another year or 2 years, whatever your sampling period is. Then you've got then we have an amber, also known as a caution. Excuse me. At that point, that shows that the asset and the fluid are still in an okay operable, and you're still able to operate them, but you may need to lower the load, resample more often, maybe do some maintenance of some form to help return that situation back to a good or a pass. But again, it's still usable. And then finally, you've got a red, which is a fail, an action, whatever you want to call it. We call it an action rather than a fail because you can still use the asset at that point still, but you're doing more harm by not taking action. So again, those actions will vary depending on what we've identified. And again, there's different severities of actions. Some of them will be take immediate action, and some of them will be we wait a month or so till we can monitor the faults and to make a determined clear asset. And in turn, this basic traffic light system is a great way of showing these actions and to allow for a confident decision from your side.
Just conscious of time, Ryan. Do you want to do one of the
Yeah,
should we
we
do
can do
one
one
of the just one of the examples rather than the
Yeah,
two?
that's fine.
You got a particular one that you want to do,
Just-
one or two?
when you bring the first one up, we can have a look and we'll see. Do you want to do this one or the next one, Andrew? This one's how the other one was fluid quality.
That's fine. You can do that one.
Yeah, we'll do this one then, Dan.
Yeah, okay.
So this particular asset had a high temperature thermal fault, which is quite hard to see maybe on the screen, but as you can see over time, the ethylene in February 2024 was still high at 240. So that then triggered our customer to resample it in June. And in that time, you can see that it's taken a significant jump from the 200 to the 1500. So then they resampled again in July, a month later, and it had gone up again. So that's a really effective way for them to see that that high temperature thermal fault was active and allowed them to then take action over, which was indicated here in our fault, that it was a high thermal fault. And as you can see, if they'd just done fluid quality, the fluid itself, okay, the acidity was fair due to it being a category B, due to its size. But if they'd only done that, they wouldn't have picked up that there was an actual fault. The fluid was fine, but there was no fault. And looking at the furans, they're at that just under that 400 mark we spoke about. So once you're there, if they had have just decided, oh, we're going to degas it rather than do some work, lost that furan data, and potentially some reclamation work can actually do more harm than good, especially when the furan has been degraded to a certain point. So again, we'll put new oil in, or we'll do some reclamation work, can cause more harm than good. And that was indicated here through this particular report, that the client, it was an active fault and that they needed to take action. It wasn't just a one-off.
Yeah, perfect.
And the next one's just a basic fluid quality. So as you can see, the acidity was high over time. With both years, it was high. But so the customer didn't take any action. But as you can see, in the first year, they hadn't done furans, but then they'd done furans in the second year. And that was significantly lower than our conservative limit of 250. So again, that reinforces the importance of knowing that if they'd have just reclaimed the oil in 2023, they'd have lost all that data and they wouldn't have known that there was a potential fault with the paper itself, and that paper has degraded. And that could have, again, as I just said, caused more damage, especially if they had decided to reclaim the oil. They potentially could have caused, especially at that point, the asset to stop working because of the paper itself being damaged beyond repair.
Yeah, I mean, hopefully, sorry to rush through those examples.
No,
it's but hopefully because of what we've covered, you can see the links between the different tests, the different output results, and then the key things we wanted you to take away was knowing the importance of the transform oil testing and the standards that apply. Making sure you're doing them to a standard is the most important thing, especially in your geographical location, if there's any differences. But make sure they're to a standard, not just an internal one. Make sure it is to a recognized standard. Hopefully you can understand that the tests that are conducted, what impact they have on your electrical safety and the reliability of your assets, and hopefully be able to interpret the oil sample results better than what you did before, and some of the mitigation strategies in order to protect your assets. So as I mentioned earlier, the next one that we're going to cover is a protection study, practical explainer, hopefully to help you understand things like time current curves and things like that. Now that's important. If you want to discuss this any further or talk through asset management from electrical side of things, get in touch and we can schedule a session. Additionally, next week we've got our conference in Chantilly, Virginia for electrical safety and reliability in the US. And if you need any more information on oil sampling specifically, we've got VPS's details there, which we can send out after, or you can get in touch with myself as well, and we can put you in touch. Yeah, thanks very much for listening. Have we got time for any questions there, Ben?
No particular questions, but there are some comments which would be interesting to share out. So Thomas put earlier, in relation to the transformer failures, although it wasn't oil but a resin core due to stress cracks caused a significant outage. I don't know if you want to mention anything on that, Dan, or any comments with that?
Well, we can't do obviously oil sample analysis in relation to that, but I think we mentioned it on the maintenance webinar last month, was around a lot of the time if you look at an oil filled asset or a fluid filled asset maintenance, like you normally do that frequency around sort of 5 yearly or determined by the conditions, but typically it's every 5 years. Often people will install cast resin or dry type transformers because obviously they haven't got a fire risk of the oil like we've covered previously. A lot of insurance companies recommend it to go against that, to go for that instead because of the oil and the flammable nature of the assets. But at the same time, it's got to match your maintenance requirements, your strategies, and your resources as well. So often, what you'll look at inside a cast resin transformer, often if you look in the maintenance, the owner manual, you're recommended to do a 12-monthly maintenance, which they're supposed to be fairly maintenance free, which is fair enough. It's a lot less invasive than an oil filled asset, but potentially in most of them, you'll see you've got to wipe it down. You've got to vacuum it out, and you've typically got to check tightness of connections, torque checks on your connections, on your tap changes, and on your cable terminations. Not on all, but on most. So it's worth checking. So often we see things where these assets aren't maintained annually, like the O&M manual directs, and it's normally left at every 5 years. And often that's where we do see a lot of failures of cast resin transformers rather than oil filled, although you do see them. And in addition to that, the environmental conditions, so where you've got dust ingress, moisture changes, humidity, things like that, is where you can potentially get tracking and get flashovers on cast resin assets.
Good stuff, thanks, Dan. And Salas also mentioned in chat earlier, online drying of oil is preferred as compared to offline.
Yeah,
If there's mention.
again, it's just down to the asset, more protections on it. So if it's a standard transformer, and that's fine, and it's not going to cause any issues. If you've got things like Buchholz relays, so you've got a conservator and a Buchholz relay, there's potential that where you're recirculating the oil, you can get air pockets in the oil, and as they go then to the highest point to escape, if they go over that Buchholz relay, the Buchholz will just see it as a pressure, and that can trip the contacts inside the Buchholz relay and trip the asset. So again, if you're running that asset and you've got an end product, whether it's distribution, generation, or production or whatever on the end of that line, if you're running that asset and it's under load, it's fine if the asset's fine for you to do that. But typically, if it's got a Buchholz relay on with a conservator, then if it trips under load, obviously there's going to be a lot of interruption there.
Thank you. A question here as well from Akeem. What is the relationship of transformer oil with G plus P or GNP?
Sorry, can you say that again, please?
Yeah,
Ben?
of course. What is the relationship of transformer oil with GNP?
Do you know, not
Can we
in
get
terms
some
of
explanation
GNP.
on G and P?
Yeah, that's the bit I'm not. It's not something we've.
If you don't mind, Akeem, just explain what you mean by GNP and we'll run through that
Please.
one.
But if not, we can get back to you on that if you share your details with Ben and that, and we can reply to you on that one.
Excellent. There's no other particular questions, but I'm looking at the time now. We've probably just exceeded. GNP fuse, Akeem has put.
Yeah, what we'll do is we'll get back to you in an email on that if that's okay, Keem.
Yeah,
Excellent.
just
Make a note of
conscious
that
of
one.
time. No, that's brilliant. Well, Yeah, thanks very much for attending. Hopefully it's been helpful. I know it's not the most rock and roll subject, but it really is helpful, especially if you're taking the step into this field or you just want to get a better understanding around how to interpret those results. It's definitely helpful. It would have been helpful for me back in the day when I stepped into the role. So hopefully it's helpful for the people on this call as well. And also thanks to VPS for supporting the call. It's much appreciated.
No, thanks for having us.